All right, so you're listening to episode number 48 of Infiltrate Radio Podcast, and I want to make an apology. We had some technical difficulties at the beginning of this podcast. We were supposed to go live, and it did not go live, and the first about, 45 seconds of the episode didn't actually record, so we sincerely apologize for that, but have no fear. The most interesting parts of this podcast were still captured, so stay tuned. We've got Michael Richmond and Andrew Robinson from RIT's Llama program. The mission of Llama is to foster the utilization and advancement of cutting-edge techniques in multi-wavelength astrophysics by RIT faculty, research staff, and students so as to improve human understanding of the origin and fate of the universe and its constituents. So stay tuned. We're going to have a little message from our sponsors stuff, and then we're going to get right into the thick of it. So stay tuned, and thank you guys for listening. This episode of Infiltrate Radio Podcast is brought to you by our amazing sponsors. Podbean is an easy and powerful way to start a podcast. Everything you need for a successful podcast. No difficult technology to learn. For our listeners only, go to podbean.com/infiltrate radio and get your first month of podcast hosting absolutely free. Again, that link is podbean.com/infiltrate radio. The show is also brought to you by Akioka Pet Boutique. Use the link posted on our Facebook page with the link to the show and use code InfiltrateRadio25 at checkout, and you save 25% on any purchase from Akioka Pet Boutique. All your pet supplies, toys, etc. So again, go to the link on our Facebook page, click on it, and use code InfiltrateRadio25 at checkout and save 25% on absolutely any purchase. In addition, we'll post the links to any products we talk about during the show, such as the drinks we're enjoying or any other items we mentioned. So if you really want to help us out and support the show and keep us going, click on any of those links we post, and the show gets a portion of the purchases that you make. So you get drinks, you get products, you help to keep the show going, and we get to not be living out on the street. So again, just click on any of the links in on any of our posts that typically go to Amazon or other affiliates. So thank you guys for all your support, and here's another episode. Infiltrate Radio.
Victor, New York.
So you can have both the best parts of breakfast at once.
That's right. That's right.
And coffee too.
Yeah, it's like a caramel coffee cake flavored coffee as well. So it's a trifecta.
I'll be over in the
amazing.
I expect a cup of coffee when I get over.
You know it.
I'm on this huge tea kick, and I've been doing Twinings of London, but I made some iced tea out of it, and I actually added, that sugar cookie Christmas tea I was drinking like 2 weeks ago.
I do remember.
I threw a couple of bags in here too, so it's like iced tea, but with like cookies in it, but no sugar or anything in it. So it's delicious. All right. So Andrew and Michael, thank you again for coming on the show. Why don't we start here? So Andrew, what is it, I guess, that you do at the research facility there? And what's kind of the purpose? Why don't we start there?
You want to go first, Michael, or shall I?
Why don't you go first? You are my boss, after all. So,
well, I'm not sure I am your boss. I'm the director of the graduate program that I mentioned, Astrophysical Science and Technology. So we have around about 40 PhD and master's students in that program right now, and a lot of our job involves providing courses for them and mentoring them in their research projects. They're all doing research degrees, so a master's is basically a 2-year degree, the end of which culminates in a master's thesis, which has to be an original research project, particular topic within astrophysics, which can be anything from studies of young stars to analyzing gravitational wave data from the gravitational wave detectors that you may well have heard about in the last few years. And then for the PhD, that's more like 5 years typically. So it's a much more involved and deeper piece of research. So that's a lot of what we do, teaching for that program, also teaching for the physics major as well. These days I mostly teach graduate courses. Michael does a mixture of both. But when we're not doing that, we're doing our own research and working with our own research students. So my particular research involve supermassive black holes at the centers of galaxies. So we now believe that essentially every galaxy, or at least every large galaxy, hosts a supermassive black hole. By supermassive, what I mean is a black hole that weighs between 1 million times and 1 billion times, or even more, the mass of our own sun. So these are really massive things. They're sitting at the centers of galaxies, and they pull in surrounding gas. Their gravitational field causes gas to spiral in. That gas heats up as it does and produces lots of light, spanning the electromagnetic spectrum, so all wavelengths from radio through to X-rays and even gamma rays. And when they're doing that, they're also growing the black hole. So as the gas spirals in, it increases the mass of the black hole, so it grows. So this is like the growth phase of the black hole. And when they're doing that, we see them as hugely bright objects. So the light from one of these things can outshine the entire stellar population, the population of stars in a galaxy like the Milky Way, by up to a factor of 100 or so. So they appear as really bright point-like things in the centers of galaxies.
So that's actually very interesting. So before Michael kind of introduces himself, so it's known as a black hole, right? So when you say it shows up as super bright, what do you mean by that? I mean, obviously there's different spectrums of light, and
yeah.
Maybe we get into a little bit of, I guess, that too. Like, how are you measuring these things? What is, when you say it's bright, I guess, what does its bright mean?
Yeah, so right, this seems like a bit of a contradiction. We talk about black holes, and by definition, a black hole, not even light can escape from a black hole. So how can we actually observe them? So it's not really the black hole we're seeing in these observations. It's light that's emitted by the gas that's swirling around them. But it's the gravity of the black hole which is the engine of all of these processes. So it's the gravitational energy of the black hole that causes the gas to shine, and it does that through atomic transitions. So atoms are made up of nuclei, protons and neutrons, and surrounded by clouds of electrons, and electrons can jump between energy levels, and as they do that, they emit light. Or electrons can swing past positively charged particles like protons, and as they accelerate, they emit light. So there are various processes which cause the light, and because of the energies involved and the amounts of material, they can produce huge amounts of light. And we're talking about light, so radio waves, infrared lights, optical lights, so visual lights that we see, our eyes can detect, through to much higher energy parts of the electromagnetic spectrum, X-rays and gamma rays.
So could I jump in for a moment here, Andy?
Please do.
Let me explain something to our listeners here. So Andy is what I would call one of the more intelligent astronomers. As he's explained to you, it's not the black hole itself that we see, it's the gas swirling around a black hole, falling in towards it, and heating up, that emits all the light we see in radio and optical telescopes and so forth. Some of our colleagues at RIT in the CCRG, which is the group of astronomers who look for gravitational waves from black holes. They look for gravitational waves, not for radio waves or light waves or X-rays. And that's really hard. It turns out seeing gravitational waves is much harder than looking for ordinary light. You've probably heard that people at RIT and at other universities using the LIGO instruments have discovered a number of merging black holes over the past 3 or 4 years now, probably something like 50 or 60 black hole mergers. The strange thing is, when a black hole meets a black hole, they crash into each other and merge into one giant black hole, but they don't emit any X-rays or visible light or gamma rays or any of the electromagnetic radiation that our telescopes can see. So those people who study black holes merging with black holes have it really tough. They can only detect those merging black holes using gravitational wave telescopes, of which there are only 3 in the world. Andy looks at black holes that are eating ordinary matter, and they emit lots and lots of electromagnetic energy that we can detect with all sorts of telescopes, telescopes in space, like Hubble Space Telescope, telescopes on the ground. So he's actually looking for the black holes that are easy to detect instead of the very uncommon merging black holes that are hard to detect.
And that's why you're saying he's smart. He's a smart astrophysicist.
I'm saying that he's an astrophysicist who's trying to avoid being disappointed, whereas all those people looking for gravitational waves, they're just setting themselves up for a very hard time.
So well, as you know, Michael, I'm also looking for wandering black holes, so black holes that have merged and are recoiling after the merger. And that's pretty hard. So I'm setting myself up for disappointment.
I have a couple of questions just from my limited kind of knowledge of astrophysics, and one of them, which is, I guess for anyone listening, I kind of have an understanding of what a black hole, and you can correct me if I'm wrong on what it is, but the way that space is, right, it's thought of like, I guess Einstein explained it as a fabric, and then the weight of whatever mass or matter or whatever is kind of causing a dip in that. And what a black hole is, it's become this infinitely dense matter that's causing basically not really a hole, but I guess a canyon in the fabric of space-time so deep that nothing can get back out of it, right? So that's kind of what a black hole is, and like you said, even light can't get out of it. I've heard that I guess the ways that those are detected is also by seeing light pass around them. Is that what you're referring to as gravitational waves? Because I don't know what gravitational wave is. I know that, like, for instance, like you can see light traveling around something. So if a star's traveling behind a black hole, you'll be able to see it kind of on the side of it, I guess, is how that is. Or I could be...
Well, so a gravitational wave, and feel free to jump in, Michael, is really a sort of stretching and compression of space-time itself. So it's not really to do with light. It's actually a ripple in space-time. So if you think about this, the idea that you, for example, you take a metal ball bearing and you have a stretchy fabric, elastic fabric, stretch tight, and you drop the ball bearing onto the fabric, then it causes a dip, which is in 2 dimensions. It's kind of similar to what you would get if any kind of mass, a planet or a star or a black hole would cause a similar dip in space-time. So you can think of gravitational waves as ripples in the fabric propagating outwards, which occur when, for example, a binary black hole, as binary black holes orbit around each other, or in events like 2 black holes merging, as Michael described earlier. So the merger of 2 black holes would cause really large ripples in space-time, which sort of diminish in amplitude as they move outwards from the place where the event occurred.
So I can try using an analogy that might make things another way to think of it. Have you, I'll ask the host here, have you ever been to a dance club
Yes. I love
Have you
dance.
ever been on a dance floor?
Yes.
Have you ever been close to those giant speakers
Yes.
play music really loud?
Yep.
So have you ever felt the sort of vibrations hitting you from the bass line?
Yep.
Okay. If you took a piece of paper and you held it in your hand right next to one of those speakers, what would happen to that piece of paper?
I would imagine it would shake and vibrate.
Exactly. So when looking for these gravitational waves, imagine you go to a dance floor and there's no music playing. You can't hear anything. But as you walk across the floor and you get closer to where the front is, you feel a sort of a ringing or a beating inside your chest, like boom, 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 boom. And if you hold up a piece of paper, even though you hear nothing, you see the paper is shaking back and forth. You're using the paper or your own body as an indirect way to sense, to feel those sound waves. That's what we do with telescopes like LIGO or Virgo, which is the European version of LIGO. We have these instruments that don't see the light coming from this black hole. But when the black hole sets up these ripples in space, as Andy has described, as those ripples go past us, they cause our instruments to shake, just like that piece of paper. And if you listen, if you listen very, very carefully, and you spend billions of dollars and 10 years building an instrument that can do that,
Right.
your instruments can sense that very subtle shaking. It's a lot less obvious than standing out on the dance floor. But that's basically what's going on, is we're using the ripples in space to hear the music, even though there is no music.
Huh. So I am a musician myself, so that has always been a draw to me to think in terms of like things like science. So it hits me almost on an emotional level because of my relationship to music. Like I grew up around music, and it's been a huge part of my life, and music is all, like you said, waves. And when I started kind of learning a little bit, and the limited amount I know, is very interesting to me, how closely related a lot of I guess even just the wave idea hits home for me in terms of how space and how the universe works. Gravity and space-time gets me a little bit. And what I mean by that is it confuses me a little bit, because I get the idea and the analogy that's put around it, the fabric and that sort of thing. But when I try to conceptualize it, because I know the fabric, but it's in 3 dimensions, right? Or all dimensions, I guess. Right? So you have a planet, so space is more like wrapped around it, right? It's not necessarily flat. And I get confused a little bit about that. But what's actually causing? So are the black holes that would be studied in that way, the gravitational waves that would come from that, are they actively moving and causing ripples? Is that what's happening, or is it, and it's causing like ripples across space-time, whatever, the fabric of space-time, or is it something else that's being detected? Or I know this isn't directly your field of study, but that just got me interested in what you were talking about there.
Can I take this? Go ahead, Andy.
Yeah, no, you do.
Okay, so
You have the question.
So if there's a black hole in space all by itself, it emits no ripples and no waves, and we can't hear it. But if a black hole happens to find a dance partner, the 2 black holes can go into an orbit around each other. And the thing about black holes is, unlike ordinary stars, they can get really, really close to each other as they orbit. Because they get so close to each other, they start emitting a significant fraction of all the energy they have. They have a lot of energy going around and around and around and around really, really fast. They emit some of that energy as gravitational waves, and that causes them to lose energy and get closer together and closer together. So they enter into a sort of a death spiral where they get closer and closer, and the closer they get, the more energy they release as these ripples in space. And the more energy they release, the closer they get. And so they, within a very short time, they spiral into each other and merge. And when they become a single black hole, they stop emitting waves again. So there's a brief time that's only, for us at the current time, only about 2 or 3 seconds long, when they're spiraling into each other very, very close, that we can sense the gravitational waves that are emitted as they merge. Before that 2 or 3 second period, we can't detect them. After that 2 or 3 second period, can't detect them. It's only in that brief period that they emit these gravitational waves.
So Andy,
I've put a link
you are
into
smart, Andy, then. I agree that Andy's smart then, because that's a very small period of time that you're able to detect.
Andy, how long is it that the two black holes will orbit around each other before they reach that point where they emit the waves we can detect? Do we have to wait 1 million years, 10 million years?
Well, I'm not sure about the stellar mass binaries, but for supermassive black hole binaries, it's on the order of a million years or so.
So for 1 million years,
so we're really only able to detect the last few seconds of the in-spiral just before the two black holes actually merge.
So for 1 million years, there's nothing. Then we might see something. Then we get nothing again. Yeah, that sounds pretty tough.
Yeah, I can imagine that being.
But I'll just add that it's not only black holes that emit gravitational waves. Essentially, everything does. So the Earth orbiting the Sun is emitting gravitational waves too, but they're just really, really tiny compared to two black holes in a close orbit.
So I guess that space is quiet, right? They say, but it seems to me from what you guys are talking about that it's actually pretty noisy with regards to being able to single out things like that. I mean, a couple of seconds within all the other stuff that's happening there. I'd imagine, you said all the planets are making gravitational waves. There's other stars out there. There's that sort of noise out there, and to filter through that, I would imagine, is extraordinarily difficult. So with regards to like what you guys are actually studying and doing there research wise, what is the reason for studying that, I guess, right? Because it's extraordinarily difficult to do some of this stuff and cost a lot of money, and some people would say, okay, well, why is it worth the money to do that? Is it worth the time to study and research these things? I guess what's the underlying truth?
The underlying question?
Yeah, you're trying to get to.
Well, one way of looking at it is to it's the question, why are we here? At the most fundamental level, it's to understand why we humans exist in the universe and how the universe came to be. So it's a question that's fascinated humanity since the first humans looked up at the night sky. So that's the fundamental reason that I'm sure Michael would agree that we do this stuff. And it's the fundamental reason that our students want to do it too. So it's a quest for knowledge. I'm not going to claim that there are sort of technological byproducts that from the work that I do. It's simply and purely a quest for understanding the universe and how it came to be and our place in it.
I think that's a good question to be answered, in my opinion. One of the things that kind of came to mind while you guys were talking too was, at what point, because black holes are essentially just massive stars, right, that have essentially collapsed upon themselves. They become so massive, I guess, right, that they end up doing that. Is there a specific point that tipping point happens, or is that dependent on the environment it's in, or is there a very specific, okay, it gets to this mass, that's too much, it collapses in on itself?
Boy,
Right,
I'm
'cause
glad you asked that question. So it turns out that, as far as we know, uh, one of the best ways to make a black hole is, as you said, to let a star collapse on itself. And that's a very unusual process. Most stars, like our own sun, they will never collapse upon themselves. Right now, the sun is being held up by the energy released by fusion inside its core. And when the sun eventually runs out of fuel in its core, it will slowly cool off and settle down and become a little burned out hunk of a star, but it won't collapse. It'll just become a cool, solid, very dense chunk of material. And most stars will do that. So most stars won't turn into black holes. The only stars that do turn into black holes are ones, I'm simplifying a bit here, are ones that start out very, very more massive than the sun, which are very uncommon. So it'd be like saying the only humans that turn into black holes are the ones that are more than 7.5 feet tall. There are some people more than 7.5 feet tall, but they're very not common. The very massive stars, when they run out of fuel for a number of complicated reasons, they can't just turn into a solid small chunk of material. The gravitational forces in those massive stars are so strong that they pull the material in on itself and form a black hole. But before that happens, there's a lot of complicated physics. And in many cases, when a star runs out of fuel, it will first start to collapse and then explode in a giant explosion called a supernova, which sends the outer layers of the star out into space at significant fractions of the speed of light, creates a giant light show, a firework that's as bright as all the stars in a single galaxy for a couple of weeks. And then the center of the star does collapse on itself to form a black hole. So the black holes, most of them, as far as we know, come from massive stars that ran out of fuel at the end of their lives after several millions of years, and then collapsed. Their cores collapsed. They blew up. They put on a light show. They spewed out their outer layers into space, creating clouds of gas shooting outwards very fast. And when I was a graduate student and when I first came to RIT, I indeed studied those exploding stars called supernovae. And so what I did was looking at the stars before they turned into black holes. And what Andy does is looking at the stars after they turn into black holes. So we're sort of a good match in that way.
A good team. That's.
I suppose so, although we don't really understand how the supermassive black holes that I study are formed, whether they initially form from single really, really, really massive stars and then grow by accreting gas, or whether they were formed by lots of smaller black holes merging together, or one giant cloud of gas collapsing on itself and becoming a black hole. So that's all of this way back in these, and we don't really have a very good idea of how they formed initially.
So when a black hole forms, obviously it's a giant star, as you said, or the majority of what black holes you know about, aside from the supermassive black holes, right? Because you're saying that we don't really truly know exactly how they form, and there's some theories around that. But the typical, let's say, I know no black hole is typical, but typical black hole, is there? It's kind of a dichotomy. There's two things there. It's exploding, but it's collapsing in on itself. So what is it trying to get to a specific size? Like, is it equalizing itself in some way? Like, why is there the explosion and that matter is being jettisoned out, and yet certain amount of the matter is collapsing in on itself? Is there like a reason?
That's an excellent question. And if you had asked it 30 years ago, people would have given you one answer. And then 20 years ago, they would have said, no, that's wrong. We'll give you a different answer. And then if you ask them now, they'll say, oh, no, that's wrong. We'll give you another different answer. When I was a graduate student, some people made models of these very massive stars, and they watched them evolve inside the computer. And then they'd get to a certain point and say, okay, at this point, it's supposed to blow up. And they run the computer models and it wouldn't blow up. It would just collapse. But we see stars blow up. So we knew that there must be something wrong with those models. In recent years, people have improved the treatment of these complicated hydrodynamical codes. And one big area of improvement is when computers got bigger and faster and had more memory. Astronomers could go from simulating them as one-dimensional models to two-dimensional models to three-dimensional models. And it turns out that there's a lot of complicated physics that works in 3 dimensions that does not work in 2 dimensions or 1 dimension. So bigger, faster, stronger computers allowed us to make better models, which help to explain why the stars explode. So that's one answer to your question. I don't think I could answer how this works in a satisfactory manner. I'll try a short one, and you can ask me questions on it, and we'll see if it works.
Okay.
So when the star runs out of fuel, there's the inner central core where the fuel was being burned to generate energy, and then there's the outer layers of the star, and then in the middle there's a middle set of layers. So the core collapses, falls in on itself due to gravity. The middle layers start falling, but a little more slowly because they're farther away. And the outer layers just sit there. It takes them a long time to figure out anything has changed at all. When the very innermost core collapses, the material falls inwards and inwards and inwards, and it shrinks and shrinks and shrinks. When it reaches a certain point, there's a physical change in the material. When the density goes from being like the density of the air in the room around you now to the density of the nucleus of an atom, which is like 10 to the 15th times more dense, there are some weird quantum mechanical effects that cause it to pause for a moment. They try to prevent the collapse from going any further. At that moment, for weird quantum mechanical reasons, the matter that had been collapsing stops for a moment and emits a huge amount of energy in mysterious particles we call neutrinos. And that stuff flies outwards, away from the center. When that huge burst of neutrinos smashes into the middle layers of the star and the outer layers of the star, it pushes them out, heats them up and pushes them out. So the outer layers get smashed into by this burst of neutrinos, and they get pushed out and fly off into space and get really hot, emit lots of energy, poof, explosion. The inner layers paused briefly for these quantum mechanical reasons, emitted a huge burst of energy, but then gravity takes over and it continues to collapse. So there's some weird brief pause that releases a huge amount of energy, and then the inner part separates and collapses and the outer part gets blown away. And that's a horrible, horrible explanation of a very complicated thing. I'm not doing justice to it.
No, it did help me kind of visualize it, at least, and the neutrino thing did help a little bit.
Have you heard of neutrinos?
I have heard of them. I couldn't explain them to you, but I have heard of them. So what is maybe help explain that to anyone listening too? Do you, if you have a good explanation for what a neutrino is?
So you know that ordinary matter is made up of atoms. Yeah. And atoms have protons and electrons and neutrons. Turns out that there are other weird subatomic particles, and one of the weirdest is these things called neutrinos. And the weird thing about neutrinos is they don't interact, they're antisocial. If you try shooting a beam of electrons through ordinary air, they get stopped by the air molecules. If you try shooting a beam of light through air, it goes through the air, but if it hits the wall, it stops. If you shoot a beam of high energy gamma rays through a wall, it goes right through the wall. But if you shine it through a tank's foot-thick armor, it stops because of the iron. Well, if you shoot a beam of neutrinos, it'll go through the iron of a tank's armor. It'll go through the wall of a house. It'll go through the surface of the earth. It'll go through millions of miles of lead. Neutrinos really don't interact with stuff at all under ordinary circumstances.
Can I ask you a question? I think I recall seeing at some point a documentary on these big underground caverns that they build with water in them, I think it is. And that's how they measure neutrinos. Like sometimes, does it slow them down or something as it goes through it? Or
so maybe 1 in a billion of the neutrinos will interact with a molecule with a water molecule.
Yeah,
so most of them
catch a very small number, and that's
that's right. Right now, as you're sitting in your studio interviewing us, there is something like a trillion neutrinos per second passing through your body, and you just don't notice because they go right through you without doing anything. Those are neutrinos that are coming from the sun, the nuclear reactions in the sun right now, because it's 6 o'clock. They're going through the surface of the earth, coming up in you from below because it's nighttime, and then heading up through the ceiling of your studio. And you don't notice a thing because most of them go right through ordinary matter. But if you wait long enough, and if you had a giant tank of water that had like 100,000 gallons, every now and then a neutrino would interact with one of those water molecules. That interaction produces a little burst of light. And if you listen and watch very carefully with sensitive cameras, you detect a little burst of light, you deduce that a neutrino hit.
So I've heard also, and again, this could be something outside of the neutrino realm, but that could be, I mean, I guess this is more biology, but could cause some of the random mutations in DNA that happen. So I don't know if it's neutrinos or radiation or something coming through and hitting or organic material and changing it in some way that causes kind of random mutations that would then, assist with what is it called? Evolution, right? So you have these random things that happen, and then those random mutations end up causing a mutation that's beneficial and so on. But would it interact with your body if it hit a water molecule within your body, potentially? Or
it's very, very unlikely. So the things that might cause random mutations in cells, for example, are more likely to be cosmic rays or particles from the sun. So most of these are kept away from the Earth's surface by the Earth's atmosphere, or more accurately, the magnetic fields, because they're generally electrically charged. So most of them don't reach the surface, and in fact, that's the cause of the northern lights, southern lights, charged particles trapped in the Earth's magnetic fields, which follow the magnetic fields to the poles and emit light as they interact with the air in the atmosphere. But
yeah, go ahead. Sorry.
Some of them do reach the Earth's surface, particularly the energetic cosmic rays that come from the galaxy. Those can be detected by cosmic ray telescopes, as well as gravitational wave telescopes and optical telescopes. And they tell us about things like supernovae. Supernovae shocks resulting from supernovae are responsible for it accelerating these. So these are charged particles. So they're like light atomic nuclei. So they could be protons, or they could be helium nuclei of helium atoms, for example, or electrons.
So with regards to what you're studying, the reason why we exist, essentially, right, is kind of the question that's seeking to be answered. And I think that that needs to be studied in like all these different fields from all different sides of things. I mean, there's not just this is going to be the answer to why we exist, right? But from your specific study that you guys are a part of, what is it about black holes that would lead you down the direction of how, I guess we came, like how the universe came into being? I mean, is there some quantum? I mean, I heard you mention, Michael, quantum mechanics a little bit. Is there additional, information that needs to be gathered about the way it works when it becomes something like a black hole? Like, what is the I guess the answer that's seeking to be found? I know ultimately, or overreaching, there's that, what is the how did we get here, right? How did the universe get here? But on the more, detailed things you're looking for, like what is it you're looking for exactly in the black holes, in the what you guys are studying there, or what you're researching?
Shall I? Or,
Go ahead, Andy.
well, first, let me say that we don't only study black holes in our group. So other people study galaxies and stars. And Michael should say a little bit about what he's working on as well. But in terms of black holes and galaxies, we believe that galaxies are intimately connected to the central black holes. And one of the reasons that we're interested in supermassive black holes in the centers of galaxies is to try to understand their co-evolution, the way that the black hole grows inside the galaxy and the effects that the growth of that black hole, because as we mentioned earlier, it releases a lot of energy and a lot of light, how that affects the way that the galaxy itself changes over time, from very early on in the universe to the kinds of galaxies that we see around us today. So, for example, the energy that is released when black holes grow in the centers of galaxies can change the way that galaxies form stars. So stars form out of interstellar gas that pervades the galaxy. Where that is dense enough, cold enough, it can collapse to form stars. And if you have an intense source of radiation sitting in the center of the galaxy, that can affect the gas and potentially blow it out of the galaxy, which would then slow down or even stop star formation. So one of the ways that galaxies are thought to evolve is through this sort of feedback process. Gas in the galaxy feeds the black hole, but the black hole produces energy because it's being fed by that gas. That energy then goes out and can disperse the gas that would otherwise form stars and feed the black hole. So one of the things we're trying to do is understand that symbiosis between the black hole and the surrounding galaxy.
And how the galaxies essentially are created, or
how the galaxies around us today, like the Milky Way has its own black hole. It's not as massive or as active as others, but it has a black hole itself.
Michael, so Andrew, or Andy, I should keep calling you Andrew. Andy, what he mentioned your field of study there, what you're doing now. What is it you're doing right now that?
So mostly what I do now is teach classes, but
Okay.
in my spare time and during the summer, I try to do some research. One of the things I do is use the little telescope on the RIT campus at the RIT Observatory to look at stars that explode and other interesting stars. That, of course, requires clear weather. And as you know, here in Rochester, we don't have a lot of that. So I only get to do that not as much as I'd like. And also the skies in Rochester are pretty bright because here in Henrietta, where the telescope is located, it's pretty close to the city and the skies are bright. You can't see faint things like these galaxies that Andy studies. So during the summers, I like to go to Japan and work with a group of astronomers there who are trying to use some new electronic detectors to look at a part of the sky. I'm not sure how to say this. A part of the sky we haven't looked at much for the last few hundred years. Let me see if I can explain this. And do you know anything about photography?
I do. Yeah. As a
Old
matter of
school
fact,
photography, like Eastman Kodak, good old photographic plates and film and stuff like that?
a little bit. So very, very little about the actual the chemistry and that sort of thing about film, if that's what you're referring to.
So do you know that back about 100, 120 years ago, 150 years ago, when photography was relatively young, you had to use these big glass plates and carry around a giant camera with the big
Indeed.
bellows, and you had to put the hood over your head, and you had to tell
Yeah.
people, don't move, because I'm taking a picture of you for the next 3 minutes.
Right.
Remember that?
Yeah.
We
Yeah.
do.
Okay, so imagine going to Africa and you're saying, I'm going to study the animals in Africa with my new photography because that's new science. And you set up your camera on the savannah and you open the shutter and you wait 3 minutes and then you close the shutter. What kind of animals are you going to see?
Yeah, probably blurs maybe, or
Yeah, or if
not
you're
even.
lucky, maybe there's a herd of zebras and they're just sort of standing around nipping at the grass. So you might get sort of zebra-shaped blurs if you're lucky. You might see elephants. I mean, they'd probably be pretty big and hard to miss, but you certainly wouldn't detect things like birds flying past you because they'd move so quickly. If you got anything, it would be just a light trail, and most of the time you wouldn't even see that. On the other hand, if you went to Africa these days with your cool cell phone, iPhone 6 or whatever they're up to these days, and you took that and you took pictures, would you see animals?
Oh yeah, of course.
For sure.
Because the shutter speed is so much faster. You can take pictures, you can take video, shutter speeds of a 60th of a second. You can see the little bird go flip, 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 flip as it goes across your screen, right? So what most astronomers have been doing for the past few hundred years, past 150 years since photography was invented, is taking pictures of the sky, and it's usually been a race to looking for fainter and fainter and fainter objects. So you build bigger and bigger and bigger telescopes to collect more and more light. And the other thing you do is you get better detectors, and then you open the shutter for 10 minutes or 20 minutes or 30 minutes, and you gather all that light so that you can detect the faintest little things at the distant edges of the universe, distant galaxies, and so forth. So, so I'm not doing that because other people are doing that. There are some astronomers at RIT in our group. One of them is Jehan Kartaltepe, who you should invite to your show sometime. And she studies faint galaxies that are very far away. And she uses the Hubble Space Telescope. She uses data from the Keck Telescope in Hawaii, which is a giant 10-meter wide telescope.
We'll have to visit there, Biz, Hawaii.
Yeah. So what these astronomers in Japan have done is they've said, well, what if there was a star that only flashed for like 1 second and then disappeared? If you're taking a picture that's 60 minutes long, you're going to add up 59 minutes and 59 seconds of nothing and then a brief little flash. And that's going to show up basically as nothing in your picture. You're only going to be seeing the things that are constant, like most stars, right? Most galaxies. But you won't be detecting things that are very brief and transient. So what they did is they built a camera out of new CMOS detector chips that are the same sort of devices that are put in cell phone cameras that can read out at video rate and are very, very sensitive. And in the past couple of years, they become big enough that they can cover a large area on the sky.
A lot of
So
people
would
know those as like mirrorless. I think a lot of cameras.
Yes,
mirrorless.
they took 84 of those chips, the biggest kind of chips you can buy from, I think it's Canon. They cost something on the order of $100,000 or $200,000 a piece. So they bought 84 of them over the course of several years, and they stuck them in a big array to make a camera that's about 3 feet across. And then they focus light from a telescope on this. I can give you for later on. I can give you pictures of the telescope and so forth.
Yeah, that would be awesome.
And they take pictures, not one every hour, but they take pictures of one every second, or even two every second. They take basically video, very slow video, of large pieces of the sky, and they look for things that blink or flash.
Huh.
And there are several types of objects that explode briefly that we know about, but they're very, very rare. What we're hoping to do is maybe to find a few of those, but also maybe to find out if there's something new, some new class of astronomical object, some weird kind of star or galaxy or gas around a black hole or something that might only emit light for 1/10 of a second or 2 seconds, and then not do it again ever, or maybe do it again next year. So you just have to be very lucky to see one of those very brief flashes.
And what are the hopes of determining from that? Is it just that, I mean, obviously you don't know what you don't know yet, and these might give you a glimpse into something that we're not aware of yet?
So that's the biggest hope. Oh boy, something new we've never seen before. Awesome, new science.
Right.
There are a couple of very unusual and uncommon known types of objects that would flash very briefly. And so it's not crazy to try this, because you know that if you wait long enough, you'll see some of these known sources. And then you can team up with people who have ordinary telescopes or radio telescopes or X-ray telescopes, and maybe put your measurements together with their measurements, and we learn more about these known sources. Things like one type of thing is called a gamma ray burst, another is called the fast radio burst.
I have heard of both of those.
So it's not crazy. Like you can convince people you're not a madman by saying, oh, we're going to look for these known things. But the real hope is to find something new and different you've never heard of before. But that's dangerous, because you could look for 10 years and never find it because it isn't there. And then you die. And then you're sad.
Right. So the things like gamma ray bursts, and I'm sorry, what was the other thing you mentioned?
Fast radio bursts. That's the newer one.
Yeah. So those, like for instance, I think like even is it pulsars, where when they were first discovered, like they're so regular that it was thought maybe this might be a man-made signal that's being broadcast. Is it super far and in between? I don't think that's the actual phrase, Biz. Few and far between, that's the phrase.
Yeah, few and far between, that's right.
That you find those, like has there been anything exciting that you found? And I find it also wonderful that in your spare time that's what you're doing, but has there I would love to be doing that sort of thing in my spare time, being in Japan looking at the universe. But is there anything super interesting that you guys have found recently that
unfortunately so far what we've done is create upper limits? And when you hear a scientist talk about upper limits, what that means is he's found nothing, but he can say they don't appear more frequently than this, or else we would have seen one. There are other things that this combination of telescope and fast readout camera can do. For example, do you remember hearing about the Hayabusa 2 space mission that brought back some material from an asteroid?
Yes, it had that aerogel stuff in it.
It had a slightly different. It had a different way of, but it was a Japanese mission that went out to an asteroid, circled it, and then landed briefly to collect some material from the surface, and then brought back that sample to Earth. So when it got close to the Earth, it was moving really fast past the Earth, and then it dropped off a capsule that came down into the atmosphere. So this telescope and camera were used to take pictures of this fast moving object, because ordinary cameras, if they take a 4-minute long picture, they're just going to get a streak. If you actually want to measure the thing going tick, 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 tick past the Earth, you have to use a very fast readout sort of system. It also turns out that one of the other things this camera can do is see meteors. Ordinary cameras just see like a streak. You open up the shutter for 10 minutes, you close the shutter, you see a big long streak. You say, some point in the last 10 minutes, there was a meteor that went by there. This telescope can watch the meteors go by, and they're doing some measurements of comparing the optical light emitted by little meteors as they enter the Earth's atmosphere to the radio bursts that are emitted when these little meteors hit the atmosphere. So there's a radio telescope nearby. They combine the radio and the optical measurements, and they learn more about the properties of these tiny little specks of dust that smashed into the Earth's atmosphere.
So what's really, and I talked about this briefly earlier, I think like it started when I learned kind of what music is and the waves, and it evolved into this interest in space and somewhat astrophysics and that sort of thing. I never actually ended up studying it or getting as deep into it as you guys have gotten, but I've gotten some questions, and being that I have the opportunity to ask to individuals that are in the field, I think I want to ask them. So bear with me if this is a stupid question. So I've watched documentaries on the beginning and the Big Bang, right? And I think that a lot of what you guys are talking about in the studying of black holes and things are, I guess, small versions potentially of what maybe the Big Bang was. And you can correct me if I'm wrong. Like, you may be able to study some of the physics that went on during the Big Bang by watching black holes. One of the things that has been bouncing around my tiny pea brain for for a couple of years since I heard it, and I don't remember where I heard it, but it made me think heavily about this. So during the Big Bang, I remember hearing that physics were at some point the laws of physics were being broken, and matter was potentially moving faster than the speed of light. And knowing a little bit about the speed of light and like Einstein stuff, and again, this is like my super limited knowledge, but as you approach the speed of light, time slows down. So you get to a point where time stops if you actually hit the speed of light, right? Because like I guess I saw something about an electron going from here to there, and in the eyes, if you were in the perspective of the electron, time would not pass between point A and point B. It would just be all at the same time. So during the Big Bang, matter was moving faster than the speed of light. So does that mean that potentially there are things, and I say wormholes for lack of a better word, but some places in the universe where potentially matter was moving back in time during the Big Bang?
No, I don't think that's the case. So early in the very shortly after the Big Bang, there was a period of, or there's believed to have been a period of very rapid expansion of space. So it's not correct to think of matter itself as moving at speeds faster than the speed of light. This period is called inflation, when the universe itself was expanding at a very rapid rate. So it's not that matter's moving faster than the speed of light, the universe is expanding. That's the idea of the Big Bang.
Because
it is true that there are timed dilation effects in special relativity. So moving clocks appear to run slow to a stationary observer, for example, and also there's a general relativistic time dilation effect, the gravitational redshift, which is, you can think of it in terms of a photon trying to escape the event horizon, from near the event horizon of the black hole. Photons have energy, but as Einstein showed, energy and mass are equivalent. So the gravity of the black hole acts on the photon. The photon cannot slow down. It has to move at the speed of light. So what happens is its frequency, the frequency of the light decreases, so that its color becomes redder. Do you have anything to add, Michael?
Well, if there were places that acted like wormholes, what would they look like? How would you find them? I believe, correct me if I'm wrong, Andy, isn't it the case that maybe 50 or 60 years ago, there were a few astronomers who said, hey, if there are black holes, which are places where material gets sucked down into these really dense objects, could there be white holes where the matter comes back out from some other location in the universe, far, far away? So fountains of matter going.
Right. So yeah, a few decades ago, that theory was seriously proposed by a number of people. Fred Hoyle was one of them, and the idea was that, as Michael said, there were, as well as black holes, you had white holes which were creating matter. It was even suggested that quasars, which are the things I study, another name for supermassive black hole, feeding off galactic matter, is we also call those quasars. So at one point it was suggested that white holes were in fact, quasars were in fact white holes. I don't know if anybody takes that idea seriously anymore. But theoretically, it is possible to have wormholes which connect different places in the universe through black holes.
And that's because of the bending of
that's because of the curvature of space-time. Yeah.
So like what, and forgive me for the Star Trek reference, but the the warp drive, right, in the Star Trek thing, is supposedly does that, right? It kind of creates those bends, like as if two black holes were kind of touching to get from point A to point B in the universe. Like that would be technically what it was.
I'll have to defer to Michael on
on the
warp drive technology. I'm not very familiar.
But I think that kind of is how I think of it. Like what you're saying there, that it might be a way to travel across the vastness of the universe. But I've also heard some talk that would take just an enormous, basically an infinite amount of energy to be able to even do that.
Yes, it's theoretically possible, but it doesn't appear to be a very practical way of getting about. Simply, as you said, because of the huge amounts of energy that would be required.
Oh, but if you do want to build some sort of space-faring civilization around that idea, you should pay attention to the black holes that Andy studies, the supermassive ones at the center of galaxies that are maybe 1 million times the mass of our sun. And you should ignore the black holes that are detected by the LIGO detectors. Those are black holes created by individual stars that are only 10 or 20 or 30 times the mass of our sun. You see, if you try to go into one of those black holes and come out the other side, if you try to dive into an ordinary one star type black hole, you will get ripped apart as you get close to it. So as you try to go in it, you'll be, I guess the technical term is, turned into a piece of spaghetti. Pulled out, spaghettification, yes. You'll get pulled out into a long, thin string of icky red stuff. On the other hand, if you try using a supermassive black hole at the center of a galaxy, you can actually go into those. You can dive in and you won't feel torn apart at all. You'll be just fine when you go in through the event horizon. Huh. And if there is a wormhole, you'll come out the other side just fine. So supermassive ones are the ones to use if you want to travel.
I'm not sure I'd try that. It would be a one-way ticket.
Unless it turns out there really is a white hole on the other side. You could be lucky.
That's right. But you'd still presumably have to pass through the singularity, which I imagine would be quite unpleasant.
Huh.
Oh, there are science fiction writers that have workarounds.
So that's the first time I've ever heard that, Michael. So what would be the experience? Because well, I guess there's two questions I had. First, as you were talking about the supermassive black holes at the center of the galaxies, obviously the reason we haven't tried to send something in is because even though it's at the center of our galaxy, it's still ridiculously far away, right? To even get there would take tens of thousands of years, probably even more than that.
More than that.
Yeah. But is it actively pulling matter into it, or is it sort of, or is everything around it, all the stars that are circling these supermassive black holes, like in an orbit that's pretty stable? Like, I mean,
is the sun sucking stuff into it?
Well, no.
You tell me.
Sort of, I guess.
Is the Earth falling into the sun? Are we all doomed? Are we going to die?
Not yet, right? Not yet. Well,
No.
who knows? It's 2021 now.
That's a good point.
But I don't know. Maybe slowly we are. I don't know the answer to that.
It turns out that black holes get a lot of bad press. Black holes, for the most part, are like ordinary stars. If you put something in an orbit around it, for the most part, it'll stay in orbit around it.
Yeah, the way I like to put it to my students is black holes don't suck. So in the sense that they're not giant cosmic vacuum cleaners. So as Michael was saying, a star could happily orbit a black hole just as the Earth orbits the sun, as long as it doesn't get too close.
You should think of black holes as wood chippers. You can stand next to a wood chipper, and that's fine. But if you put your hand into the wood chipper, bad things happen. So just don't put your hand into a black hole.
I'll try my best to avoid doing that. But why? So why is it different? Why are the supermassive black holes then different than, let's say, a smaller black hole when it comes to like the event horizon, which and actually falling into it?
Well, you go, Michael.
So this is going to be the portion of your podcast that involves a small amount of math. So you may want to tell, if you're at home with small children, you may want to tell them to just, turn to a different channel for the next 2 minutes. You may recall that there was a guy named Newton who came up with some laws about gravity.
Yep.
And one of those says the strength of the gravitational field goes like g/m over r squared.
Exactly.
So there's a 1 over r squared. So you have to divide by your distance squared. If you divide by a big distance, you get a small number, and the force of gravity is small. If you divide by a small number, you get a big force of gravity. So if you have a very big object, when you try to stick your hand into it, you are far away from the center. In that gravitational equation, there's a 1 over r squared. The r is your distance from the center. If it's a big, big black hole, you're far away, it's a big R, you divide by a big number. The gravitational force at that moment, when you first try to get in, is small. You're not ripped apart. If you find a small black hole so that you get closer to the center, then that 1 over r squared is 1 over a small number, and then that becomes a big force. Black holes are only dangerous if you can get close to the center. And a star-sized black hole, you can get within about 3 or 4 miles of the center. So that's pretty close. One of the black holes that Andy studies, you're probably 3 or 4 million miles from the center. And that's not very close at all. And so it doesn't tear you apart at first. If you kept falling towards the center, eventually you'd get close, and that would be bad. So that's the end of the math part of today's podcast. You can tell your children to listen again.
Okay. Well, my older brother, hopefully he's listening. He's a math major at Hunter College. I think he teaches too. So he he might know that. But I think I get what you're saying. So kind of like like the more that, or the closer you get to it, the stronger the force is at the.
That's right.
So you probably heard of a thing called the event horizon.
Yep.
So
Yeah,
that's the boundary that within which nothing can escape the black hole, including light. So that increases in size. It scales with the mass of the black hole. So the more massive the black hole, the larger the event horizon, the bigger the distance from the center to the event horizon. So as the black hole gets bigger and bigger, the event horizon gets also bigger and bigger. And so the gravitational force near the event horizon becomes smaller for the bigger black holes, the more massive black holes.
I learned something today, Biz. Every day you can learn.
Only something.
Well, there is a downside before you all try going out and finding a galactic massive black hole and going into it. As far as we understand, for the most part, if you succeeded in finding the black hole and standing next to it and then sticking your hand in, you wouldn't feel bad, but you would get pulled closer in and closer in and closer in. And eventually you'd get close to the center and you couldn't escape. So eventually, unless there was some weird wormhole science fiction-y thing, you would get pulled apart. It would just take a while.
Yep.
So you probably don't want to try this unless someone assures you that the black hole you've chosen really is connected to another black hole in a distant part of the universe, and you really will pop out the other side.
In one piece.
So let me ask you this, because I have another question now. So and we're coming up. We're almost an hour and 15 minutes. So, but one of the questions I have is, I know again, I'm just every little bit of science that I know I'm gonna bring out here. So I know that, like, for instance, with the sun and the solar system, as you move out, I guess the expectation or previously the expectation of how much gravitational pull the sun has ends up being more than was expected. If I could be wrong in that. So what I mean by that is, like, I don't know where I was going with that. Like it like as if there's more gravitational force than the matter that exists.
I think you might be talking about the dark matter problem.
Yeah, dark matter. So that it shouldn't be as much gravitational force per the amount of matter that's there, and so there's some, I guess, question. Like, I think it's referring to dark matter, dark energy, and that sort of thing. I think dark energy is different.
Yeah, so the basic idea here is that rather than the sun, but if we think about the galaxy, you can measure the light from the stars in the galaxy, and you can estimate the amount of mass that has to be there to produce that light in the form of stars. So, and you can measure the speeds at which the stars and gas clouds are orbiting the center of the galaxy. So what you find is, for a galaxy like the Milky Way, that the stars and gas clouds and so on are moving around the center of the galaxy at a rate that is faster than you would imagine or calculate if you just count the mass that is required to produce the light that you measure. So in other words, there isn't if you just measure the mass by calculating it from the light that you measure, there isn't enough mass there in the outer reaches of the galaxy to explain the speed at which stuff is orbiting the center of the galaxy. So it is thought that there must be mass there, but we cannot see it, so we can't measure its light. And that's what's known as dark matter. and we still don't really know what it is. There are a number of different ideas about what it could be, but nobody's really identified what it actually is. So possibilities range from lots of tiny stars that are just very, very dim to exotic fundamental particles.
Interesting. And I know you had stated that it's not a giant vacuum, right? Or not like a vacuum, hoovering in a bunch of matter
Black
from
hole, right? Yeah.
from the surrounding area. With relation to from galaxy to galaxy, is there something that is known that is keeping galaxies in some sort of relation to each other, or are galaxies kind of just floating out in space and moving away from each other? Because I know what you were saying is that it's not hoovering in mass or matter or whatever, and there's not enough gravitational force, I would assume, from that to pull in other galaxies.
So it's interesting that you jump to other galaxies. The very first evidence we had that there might be more gravitational force than ordinary stars could produce came from observations of galaxies back in the 1930s by an astronomer who was a very strange Swiss fellow who got angry a lot. Anyway, he noticed that in one cluster, several clusters of galaxies, the galaxies were zipping around as if they were being pulled by the gravity of other galaxies. But when he added up all the mass from the galaxies he could see, that wasn't enough. As Andy said, there must be other mass producing that extra gravitational force. And people at first thought he was crazy, but over the next 50 years, more and more evidence was gathered that showed that, not only in ordinary galaxies, in galaxy clusters, this dark matter or invisible matter problem occurs all over the place in the universe.
All right. Well, I think we are coming up about an hour and a half, and I wanted to kind of talk a little bit just about you guys personally, if you got some more time here, just a few more minutes. I guess we'll start with Andrew. How did you end up getting into, or Andy, how did you end up getting into astrophysics? Like, was it something that you were always interested in from like the time you were a kid, or was it something that you kind of slowly?
So I did a physics bachelor's degree in the University of Manchester in the UK, and it's true to say that I wasn't particularly interested in astrophysics or astronomy when I started, but I happened to take an elective course, and the course was on the interstellar medium, that is the gas that fills the space between the stars and galaxies. And I found it fascinating that by understanding this gas, by taking observations of it using devices called spectrographs that split the light into different wavelengths, and at certain specific wavelengths, you see what are called emission lines, at other wavelengths, you see absorption lines, so peaks and dips in the spectrum. And those peaks and dips are caused by electrons jumping from energy to between different energies in atoms. And you can analyze these spectra and determine all kinds of things about the properties of the gas. And I found that fascinating, that you could learn about the makeup of very distant galaxies by observing and analyzing the light from them.
Like the spectrum, where every light is a different color because it's different wavelengths, right?
Yes, exactly. So I found that fascinating, and that's really what got me interested in pursuing astrophysics. So I went on to do a PhD, and the PhD was on active galactic nuclei, so supermassive black holes in the centers of galaxies, and I'm still working on them now.
And Michael, how did you end up getting into to become bedfellows here with Andy and the what is it, multi-wavelength astrophysics? I struggle with the word multi-wavelength.
Multi-wavelength astrophysics.
Wavelength, yes.
So when I was in college, I'd liked all sorts of sciences when I was growing up. Probably I wanted to study dinosaurs more than anything.
Yeah, me too. That was my
Was it? Yeah.
passion.
I still like to read about dinosaurs whenever I can. I attended a remote session well, anyway. When I was in college, I was trying to decide between physics as a major or astrophysics, because the school I attended had both. And it turned out that the student faculty ratio was something like 50 or 60 students. There's like no, more like 20 to 1 in physics. So there are 20 students for every faculty member. And it was like 1 to 15 in astronomy. So when I was a senior, I was the only person in the astronomy department as an undergraduate, and there were 15 faculty members. So I figured, oh, I'll probably get a lot more attention if I go with this astronomy thing than with physics. Also, at that time, that was back in the days when there were mainframe computers with terminals, you know, and in the physics department, there was this one room which had a bunch of terminals that undergraduates could use, but there were always these students fighting for them. Like, oh, as soon as one would open up, someone would jump in. And there was a room with about 8 different terminals in the astronomy department, and there was no one using them most of the time. So I could use the computers whenever I wanted, which was good because there was this one really cool game called Rogue, which was really fun to play. So for those reasons, those excellent reasons, I decided to major in astrophysics rather than regular physics. And then I got stuck in a rut and just couldn't stop.
Right. So let's do this, because I'd like to talk. I'm going to obviously post the link to the the research that you guys are doing at RIT, and if you want me to post any other links to any other research that's going on, if people are interested in kind of diving a little further into what you're doing over there. But is there anything in particular that's being worked on now that is interesting that maybe some of your students are working on and getting into?
Gosh, that would take quite a bit of time.
A long time.
Yes. So I'll try to keep it brief. So our group is working on a number of different projects. So Michael works with me, but also has his own thing which he talked about earlier. So I have students now who are working on understanding dust around active supermassive black holes in galaxies. So just as there's dust on your mantelpiece, there's dust in space too. It's made up of grains of graphite and silicates, and it absorbs light from the gas around the supermassive black hole and re-emits it in the infrared part of the spectrum. So one of the things we're trying to do is understand the distribution of that dusty gas. And one of the reasons we want to do that is because it absorbs light at optical and ultraviolet wavelengths and basically blocks us from seeing the light that comes from the quasar. So we want to understand the arrangement of the dust around the center so that we can better understand the circumstances when we can see and can't see the light from the supermassive black hole. So we have a couple of students working on that aspect. The galaxy I have in my background, this is emerging, so it's actually a galaxy merger. So the 2 galaxies which are merging together, and each of those galaxies has a supermassive black hole. So I have another student who's analyzing spectra from galaxies like this one in order to try to understand whether the energy is coming from star formation, so stars forming in the centers of these galaxies, or whether it's coming from a supermassive black hole. So as Michael put in the comments, a galaxy merger is basically a cosmic train wreck. So we're talking, but you talked earlier about galaxies sort of floating in space. They don't really float in space. They're actually interacting gravitationally with each other. And when they come close enough, they can smash into each other and create a whole new galaxy when everything is settled down. So that's another thing we're working on. As I mentioned earlier, we also have students working on displaced black holes. So black holes which are not actually sitting in the center of the galaxy, but are actually wandering through the galaxy. And the reason they do that, we think, is because when two galaxies merge, eventually a binary black hole forms in the middle, so two black holes orbiting each other. They can merge and produce gravitational waves, as Michael explained earlier. But because the gravitational waves don't go out equally in all directions, the gravitational wave pulse is stronger in one direction than in another direction, the merged black hole gets a kick, gets a recoil, like the recoil of a gun. And that causes it to move out from the center and bounce around in the merged galaxy. So we're looking for evidence of that.
Yeah, I think there's we could probably talk forever. I'm so interested in what you guys are doing over there, and if you have students that are interested, I'm sure our listeners would love to kind of hear what they're working on too in more detail. We're going to skip the news corner, and I think that anyone watching this, anyone listening, I think you guys have had enough of the news. So for a week, we're going to give you a week off of that, but. Kind of in regards to what's going on, we're moving to a new administration here, coming from another administration, and obviously you guys have been doing this for long enough. As this goes on, as the country changes from one president to the other, one administration to the other, do you guys see any direct result of like differences in administration when it comes to your research and what's happening? Like, do you feel a direct impact from any of that, or is it something where your projects are being funded outside of the government space, and so that's not really a direct?
No, we're very dependent on federal funding. So most of our funding comes through NASA or through the National Science Foundation. So it really does depend on the priorities of the current administration as to whether they're going to invest in sciences, and also the priorities of those agencies, NASA and the NSF, as directed by the administration, as to where they should put their funding. So obviously NASA has many roles, and one of them is astrophysics research and building things like the Hubble Space Telescope and the soon to be launched, we hope, James Webb Space Telescope, the Hubble successor, which should be launched, we hope, next year.
Yeah, and that's supposed to be bigger, better than the Hubble. Is that?
It's going to be a lot bigger, 6.5 meters across as opposed to 2.4, and it will certainly be able to resolve to give us much more detailed pictures of the universe than Hubble can.
When do you guys know offhand? When was the Hubble telescope launched into?
1989.
So 89. So the difference in technology from then to now, I suppose, is pretty significant in terms of a difference in that. Like you were talking about the CMOS sensors and things like that didn't even probably exist really back then. I'm really interested to see what in the next the next 10 to 20 years, kind of what comes about from research like what you guys are doing, and hopefully the sciences and these projects continue to get funded in future administrations, because regardless of politics, I think it's something that we all benefit from. I mean, even the fact that we're here, we're all on camera, and we're going across the internet, probably some of us over Wi-Fi. I think I'm over Wi-Fi, so that's a light or wavelength there. So we all benefit from the research that happens from that, and I hope in my lifetime. I mean, I don't think that it'll probably happen, but that we have more answers to how this how this all started, and maybe one of you guys, if you find out that answer, you email me. And let me know.
I have to admit that's going to be pretty. If I found out the answer, emailing you would not be the first thing I would do with the information.
All right,
sorry to break it to you.
Yeah. No, at least you're honest, Michael. I appreciate it. But I want to thank you guys for coming on the show. I know you guys are busy, and we really appreciate it. Any closing things you guys want to get out there into the public, and any way people can assist with what you guys are doing or look deeper into?
I'd like to point out that in 2024, which is 3 years from now, in April of 2024, a total solar eclipse will be visible from here in Rochester. You won't have to travel around the world to see it.
Ooh.
So mark that on your calendar.
Are we talking early or late April?
I think it's around April 8th. You can look it up. If you just type solar eclipse Rochester 2024.
Fantastic.
I can't do that at the moment. So that's something to keep in mind.
Yeah, I know we had a rough time with the Jupiter, and
yeah, we had a very rough time with that. I was all ready.
Yeah.
I was out there.
I was ready to take a look too. I just saw something too in the speaking of, I know we're not doing the news directly, but something about FM radio transmissions coming from Jupiter. Have you guys heard anything about that? I saw some sort of news story, not like being made, but it's some sort of FM signal coming off of it from something. But you marking that down in the calendar, Biz? We can do like an eclipse show.
Oh, what you should do is mark it down for 1 year before the event. You can have a podcast 1 year in advance so that you can talk all about it, and then do it like a week in advance of the actual event.
All right.
Put down those 2 dates.
Excellent. Biz is writing it down as we speak.
Yeah, I'm getting there. Here we are.
All right, so I'll post the link to your research. Thanks again, guys, for coming on the show. I really appreciate it. And I feel like I've had a really great conversation here, honestly. I know a lot of us are locked down. And before I let you guys go, are you being hampered at all by what's going on with the lockdowns? I mean, are you guys allowed to still do a lot of what you're doing research-wise?
Yeah, well, fortunately, in our case, a lot of the research we do is computer-based. So we don't need to be in a lab. Michael works at the observatory, but that's a pretty lonely place at the best of times, I guess.
Well, actually, normally I have to but I have to allow students who are taking introductory astronomy lab classes at RIT to use the observatory. So under ordinary circumstances, I can't use it 3 nights a week. But since there are no introductory astronomy lab classes because of the pandemic, I actually get to use it anytime.
All the time.
So this is the one silver lining in the pandemic for me and for no one else.
Is that's I'm supposing that's probably not open to the public, right? It's pretty
it's not open, certainly not open to the public now, but under ordinary circumstances, we have occasional public nights,
really?
2 or 3 times a semester, when we invite people to come and look at the telescope. We can't do that now.
Yeah. What is the what it's looking at being displayed on some sort of a screen? Like how are you actually viewing?
Oh, I want you to look with your eye through the eyepiece.
Oh, so you
can look on a screen right now in your studio and you can see things on a screen.
Yeah.
Where's the excitement there?
Oh, absolutely. So, but it's just, how big is the actual telescope that's there?
Big enough.
Yeah.
Yeah, it's we have several telescopes, 12-inch, 14-inch, 6-inch, 8-inch diameter telescopes.
I'm guessing
they'll show you the craters on the moon. They'll show you the rings of Saturn, show you the moon's Jupiter.
Huh.
So wait another year for this whole thing to die down and come on out.
All right. Well,
let me also imagine RIT. I don't know if you guys have heard about this event, but it's generally it occurs in late April or early April, I think, is the scheduled date for this year. So it's an event where the campus is open to the public, and there are all kinds of displays, demonstrations spanning arts and sciences, most of them put together by the students. So it's a great day out. I don't know whether it's going to happen or what form it will take this year because of the current circumstances, but hopefully next year.
Okay. All right. Well, we'll post a link to that. I'm assuming there's something there, or maybe not an actual date at this point, but I'll definitely post to it. And again, I know you said your laptop's about to die, so we'll wrap up here. I had a great time talking to you guys, honestly. And if you
very informative.
Yeah, come back on the show and talk about anything you're doing. I do ask our audience, to email us if you liked what you were hearing here, and to in any way that we can, we'll help support and get the word out about what's going on at the research facility. And good luck to you guys, and stay healthy, stay safe. And we will talk to you soon. So this was episode, what was it again? 48.
48.
With Michael Richmond and Andrew Robinson. And I don't have the thing queued up, Biz. So I'll add it on the YouTube.
Terrible.
Yeah.
Terrible.
But thank you everyone for listening. And you're listening to Infiltrate Radio. We will talk to you next week.